Hi, my name is Luis Castaneda, and this is my project for CS230 about wafer map interpolation. In the semiconductor inspection industry, tall 3D NAND structures present several problems. The largest one being keeping the wafer surface at an optimal distance from the inspection optics to maximize sensitivity. One solution to this problem is to create a topographical map of the wafer surface at inspection time. However, this can be a very time-consuming process. The goal of this project was to show that we can reduce the amount of data collected and interpolate the missing data using a deep neural network. I've done this through a two-step process. Step one was to use a partial convolutional network to learn the context from the available data and fill in the missing regions. This is like other in-painting image tasks which are typically used to repair damaged images or remove unwanted objects from an image. In this case, I'll just be filling in the missing data with the surrounding context. I implemented an architecture developed by the NVIDIA Corporation based off a standard U-Net network. Each layer will derive some context and then pull the image until we reach the bottleneck, at which point the original image of 512 by 512 has been reduced down to 4 by 4. We'll then work back up the network with skip connections until we arrive at the original image size. At each step on the way down, we reduce the mask size, and at each step on the way up, we fill in that mask through partial convolutions on the valid data. Step two was a simple image upscaling done with a fast convolutional network with the addition of a bicubic skip connection. This network learns the context at each filter level and then combines it with the bicubic skip connection at the very end. The bicubic image provides the base, while the network enhances the context and the contrast. This step results in a higher resolution image, which accurately captures the wafer pattern. One of the major challenges of this project was the limited amount of data available. Data was collected on a few customer wafers, each of which only had a half dozen or so mappings collected. These mappings were then converted from their original format into images for processing. Each of the images was manipulated in several ways, including blurring, flipping, and other linear transformations to augment the total dataset. In total, there were 360 images used for training, 40 for development, and 40 for tests, all randomly sampled from the total dataset. To validate the results, the images were converted back from their original format and then compared to raw wafer maps. Here you can see that the error between the interpolated data and the raw data is held to within 0.1 microns, which is acceptable for a use case. Although the accuracy of the results were acceptable, the overall processing was longer than the 1.5 minutes that it normally takes to collect the data. This project demonstrated the process is feasible, however, there are a few optimizations that we'll need to make it production worthy. For example, the network used for in-painting could be reduced given that there's only one channel of data and the context is simple and periodic. Additionally, upscaling could be integrated into that same network, further streamlining the process, and that's what I hope to follow up on in the coming months. Thank you for your time.